Chapter 4 Higher Order Differential Equation, Section 4.1 Preliminary Theory Linear Equations. So in this lecture video we will basically discuss preliminary theories of linear equations of higher order differential equations, and in the next videos we will talk the method to solve the higher order differential equation. Alright, so the primary goal of this chapter is to find the general solution of a linear higher order differential equation. So there are two types of problem: initial value problem and boundary value problems. So let's look at the initial value problem first. For a linear differential equation, an nth order initial value problem is of this one. So this is linear because you can see y prime and n minus 1th derivative and nth derivative of y, the degree of those functions are just 1, and the coefficients are a function of x, so it is linear. And it is nth order differential equations because the higher order is n, and it is initial value problem because we have initial conditions, n initial conditions. So this is a linear nth order initial value problem with n initial conditions. So we always have for example, if it is a second order differential equation, then we will have two initial conditions. If it is third order initial value problem, then we will have three initial conditions. Okay, all right, so you can see initial point is at x equals x naught, so the value of y at x naught is y naught. Y prime, the value of y prime at x naught is y1, and the value of y n minus 1th derivative of y at x naught is y n minus 1. So there are n initial conditions. So this is called initial value problem. Let's look at the existence and the uniqueness of the solution of initial value problem. When does the solution exist and when does it is unique? So there are three cases here. If an minus 1x, and so on, a1x, a0x, and g of x are continuous on an interval, that means these coefficients and gx are continuous, okay, on an interval. And the next property is a and x not equals 0. This means that the coefficient of nth derivative should not be equal to 0 on that interval. And the third is if x equals x naught is any point on this interval, then we say that the solution of the initial value problem exists and unique on that interval, I. So if these three conditions holds, then we can say that this initial value problem has solution and is unique. So let's look at the example here. So this is the initial value problem. You can see this is the third order differential equation with the three initial conditions, and this possesses a trivial solution y equals 0, and this is the only one solution it possesses, because when you substitute y equals 0, y prime, y double prime, and y triple prime into the given differential equation, it satisfies, as well as it also satisfies each initial conditions. Okay, or you can check whether these three conditions holds or not. Okay, so you can see the coefficients here of these differential equations are 3, 5, -1, 7, which are constant and is continuous because constant functions are continuous on R. And g of x is 0, which is again constant and is continuous. Now the next property is a and x. Here a, 3, of x, or a t, you can write t, okay, or x. So this is 3, which is not equal 0 on the real line for every t belongs to R. And the initial value is t equals t naught, which is 1, which also lies on this interval from negative infinity to infinity, or you can say real line. So these three condition holds on this interval or negative infinity to infinity, or you can say throughout the whole real line. That's why y equals 0 is only the one solution on this interval, negative infinity to infinity. Okay, all right, so we are just checking whether there exists solution, and that is whether that is unique or not. Okay, so for another example, let's take another example. Find the largest interval on which the conditions of the theorem satisfied. Then we can say that there exists solution, there exists unique solution, right? So on that interval, so let's see. So this is a third order differential equation, linear differential equation, third order linear differential equation. So you can see this is my a3t, and here a2t, which is 1, and this one is a1t, and excuse me, I just made a mistake. Let me erase this one when I was mentioning a2. So this one is my a2, right? This one is my a1, and this one is a0. Okay, and g of t is 0. So this is my g of t. Okay, and you can see this is a quadratic function, t square minus 3t, so it is continuous on real line, so it is continuous, right? And then 1 a2 a1t is just 1, which is constant, and it is continuous on real line, and a0t is this one. This is a linear equation, and which is continuous on real line, or you can say negative infinity to infinity. And g of t, which is 0 is constant function, and this is also continuous on real line. So they are all continuous from negative infinity to infinity. Let's say that there is a 0, or you can say on the real line. Now the next, so the first property holds, right? a2t, a1t, a0t, and g of t are continuous on negative infinity to infinity. All right, throughout the real line. Now the second property is a2t. Let's whether this a to t equals 0 or not. Okay, so let's say it, because a to t is a quadratic function, let's say that this is equals 0. Okay, so a to t is t square minus 3t plus 2 equals 0, and this is a quadratic, so you can solve or find the values of t by any method. So I'm just using a factoring method. So its factor is t minus 2 times t minus 1. You can factor this one, and I can see that either t minus 2 equals 0, that gives us t equals 2, and t minus 1 equals 0, that gives us t equals 1. So when t equals 2 and when t equals 1, this function will be 0. Okay, a2 t will be 0. So that means except, okay, when t equals 1 and t equals 2, except these 2 points, everywhere is the quadratic function's value would be not equal 0. Okay, so except these 2 points on this interval. So that means from negative infinity to 1, and 1 to 2, and 2 to infinity. So let me change the color. So on this interval, a to t will not be 0. On this interval, a to t will not be equal 0, and on this interval, a to t will not be 0. Okay, all right, so let me write it down. A to t will not be 0 on negative infinity to 1, 1 to 2, and 2 to infinity. Right, so this is the second property, number 3. Now we need to find whether that initial condition lies on that interval or not. Okay, so we can see the initial value t naught is 0. T naught is 0, so t naught equals 0. So 0 lies on this interval, so we can only pick this interval. Okay, so this t equals 0 belongs to negative infinity to 1. Thus, by theorem, we can say that, however, this function is continuous throughout this line, real line, but a to t is only not equal 0 on this interval, and t naught lies on this interval. That means this is the largest interval where initial condition lies and a to t not equals 0, and all these functions are continuous. So thus we can say that I equals negative infinity to 1 is the largest interval on which the initial value problem has unique solution. So the unique solution cannot be in this interval because the initial condition does not lies. However, this properties holds, and in this interval, again, that will not be the in that interval there will not be a unique solution because initial condition does not lies on that interval. Initial condition lies on that interval, and on this interval these functions are continuous. On this interval, a to t is not 0. That's why negative infinity to 1 is the largest interval on which initial value problem has a unique solution. Okay, so that's how we figured out. Let's look at another example that will be that will help you to be a little bit clear. All right, so again, you can see this is here we have a second order linear differential equation, which is initial value problem, because you can see initial conditions. There are two initial conditions. Okay, so first, which one is my a2? This is my a2, a2t, and here a1t, and a naught t is 0 because we don't have that term, so 0, and this is my z of t, which is 0. So they all are continuous on real line, right? So let's say that this is my real line t. All right, and then I will again draw this y-axis as well because I need to draw sine t. All right, so they are all continuous throughout the real line, so we don't need to be worried about that. Number 1 holds on throughout the real line. Number 2, a to t. Okay, so let's just set whether this equals 0 first, but we are looking the interval where this a to t is not 0. First of all, let's set this equals 0. Okay, to see the second property, I'm going to set a to t equals 0. So a to t is sine t equals 0. So when does this sine t will be 0? So this will be 0 when t equals n pi, where n is integer. That means, you might know that the graph of sine t would look like this. All right, so this is 0, this is pi, this is 2 pi, this is 3 pi, this is 4 pi, and minus pi, minus 2 pi, minus 3 pi, and so on. So the sine functions are 0 at these points, right? So we have several intervals. So on this interval, sine t is not 0. On this interval, sine t is not 0, and except those points. Okay, so there are several intervals where sine t is not equals 0. But the main thing is, okay, let's just set a to t not equals 0 on all these intervals, but we will figure out which interval is the required one. So let's just jump into the next property, the initial value problem. So the initial point, which is t equals 3 pi over 2, where does it lies? On which interval it lies? Let's look at. So 3 pi over 2, so 3 pi is here, so 3 pi is here, right? So the half of 3 pi, that means somewhere here. This is 3 pi over 2, and that 3 pi over 2 lies in this interval. That means this belongs to pi 2 pi on that interval. That means, okay, and a to t will not be 0 on this interval. I'm just picking that interval because however a to t will not be 0 in all these intervals. I'm just picking that interval because we are looking the interval where the initial condition also lies. Okay, all right, so thus we can conclude that pi 2 pi is the largest interval on which the condition of theorem satisfied. So therefore pi 2 pi is the largest interval, or you can say is the interval solution, is the largest interval where the solution exists and unique. Okay, all right, so let's look at, okay, we have discussed about the initial value problem, and also we have discussed about the existence and uniqueness of the solution of the initial value problem. And we also have a boundary value problem. You know, boundary value problem is similar to the initial value problem, but the difference is here. The main difference is here it says that the dependent variable and its derivatives are given at more than one, more than value of the independent variable. Okay, so let's look at the problem. So this is the DE, but the conditions here, you can see that y at A is y naught, and y at another point, more than one independent variable. That means another point B is given y1. So, and these conditions are called boundary conditions. So this problem is actually the boundary value problem. Okay, and the solution of the boundary value problem would look like, so these are the solutions of this differential equation, all these solutions, but the solution of the boundary value problem are this one and this one, because they are passing through these 2 points, a naught y naught and b naught b y1. So these two are the solution of the boundary value problem. And let's look at another example here. So you can see this is the second order differential equation, and you can see the conditions here. X at 0 is 0, and x at pi over 2 at the different point, right? At the different independent point is 0. So when you look at the initial condition, let's go up. So you can see this initial condition y at x naught, y prime at x naught, so they are at the same point, right? The initial condition are at the same point, but here you can see these conditions are at the different points, so more than one point. Okay, so this is called the boundary value problem, and this one is boundary conditions. So that's the main difference between initial value problem and the boundary conditions, boundary value problem, I'm sorry. Now once we figured out the initial value problem and boundary value problem, let's look at the homogeneous equation. Nth order excuse me, nth order linear nth order differential equation is of this form, is called homogeneous. So you can see the degree of y and its derivative is just 1, so this is linear because the coefficients are all function of x or constant, so it is linear, nth order linear differential equation. And here you can see on the right side this is 0, so that's why it is called homogeneous. Whereas this equation is same, but on the right side you can see g of x, where g of x is not equal to 0. Then that type of differential equation is called non-homogeneous. If this g of g is 0, then it is called homogeneous. If this g of x is not 0, then it is called non-homogeneous equation. Okay, so let's look at the 5 facts about the linear homogeneous ordinary differential equation. The linear homogeneous ordinary differential equation always has a trivial solution y equals 0. You can check by plugging this here. Y is 0, y prime will also be 0, y and nth derivative of y will be 0, and that will be the sum of that, and these coefficients with these coefficients will also be 0, so it satisfies the differential equation. So linear homogeneous differential equation always has trivial solution. And the second fact is, if y, non-trivial solution y, is a solution, then the constant times y is also the solution. Okay, you can plug it and then check it. If the next fact is, if y1 and y2 are the solution, then c1 times y1 plus c2 times y2 is also the solution. Okay, number 4, an nth order homogeneous linear ordinary differential equation possesses an linearly independent solution. Let's say that y1, y2, yn. Then the set of y1, y2, yn is called fundamental set of solution of that homogeneous differential equation. So be careful with this one. N linearly independent solution, then this set is called fundamental set of solution of that linear homogeneous differential equation. Okay, and the general solution, the fifth fact is, general solution of that linear homogeneous equation is y equals c1 times y1 plus c2 times y2 plus up to cn yn. Okay, so this is the general solution. All right, so so those are the 5 facts about the linear homogeneous ordinary differential equation. Let's look at another term. We define nth order differential operator as follows: nth order differential operator, okay, differential operator or polynomial operator to be L. Okay, so this can be defined as just L. Oh, I forgot to erase this y. Okay. All right, this is considered as nth order differential operator. All right, now nth order differential operator, this L is linear operator. When we call this L linear operator, if it satisfies this property, L of alpha of f of x plus beta times g of x equals alpha times L of f of x plus beta times L of g of x, where alpha and beta are constant. So if L satisfies this property, then we say that this L is linear operator. Okay, All right, so let's look at another term, superposition principle. Let y1, y2, yk be the solution of homogeneous nth order differential equation on an interval I. Then the linear combination of that solution is called the is also a solution, and is called the superposition principle. So by superposition principle, y equals this is also a solution. Okay, that means we multiply the each solution by constant and add them. That is called superposition principle. So for example, let's say that this is a function y1 and y2 are both solution of this homogeneous linear differential equation on an interval 0 to infinity. Then by superposition principle, we can multiply this solution by c1 plus and add c2 times this. C2 times this is also a solution on that interval. So by superposition principle, we can say that y equals this is also the solution of that differential equation on the interval 0 to infinity. Okay, and let's look at linear dependence and independence. What is a linear dependence and independence function? A set of function f1x, f2x up to fnx is said to be linearly dependent on an interval I if there exists constant c1, c2, cn, not all zeros, such that c1 times f1x plus c2 times f2x plus up to cn fnx equals 0 for all x on that interval. Okay, if the set of function is not linearly dependent on that interval, then it is said to be linearly independent. Okay, so let's look at what type of functions are linearly dependent and independent. Let's say that we have a function f1x, f2x, f3x, and f4x, which are defined as follows. And these are linearly dependent because you can see f2 can be expressed as follows: 1 times f1x plus 5 times f3x plus 0 times f4x. Or we can subtract both sides f to x, then we will get this relation. You can see this is my c1, this is my c2, this is my c3, and this is my c4. If I choose c1 equals 1, c2 equals -1, c3 equals 5, and c4 equals 4, and their linear combination will be equals 0, right? And these c1, c2, c3, c4 are not all 0, right? So that's why if I can express into this form, that's why we can say that this is linearly dependent, right? So here we had 4 functions, right? Okay, all right. Now we have here 3 functions, 1, 2, and 3 functions. Let's check that whether these functions are linearly dependent or independent on the interval -infinity to infinity. All right, so let's write it in a linear combination: c1 c2x plus c2 x squared plus c3 5x squared minus 4x. So let's choose. So if I choose c1 equals 2, because I'm choosing, how I am choosing is I can see 2x here, here I can see 4x. If their coefficients are same with the opposite sign, then they will be cancelled, right? So if I choose c1 equals 2, then it will be 2 times 2x will be 4x. And if I choose c3 equals 1, so this term will give us 4x, and this term will give us -4x, and that will be cancelled out, right? So if I choose c1 equals 2 and c3 equals 1, then this term will be cancelled out. Now the rest is this one and this one. So if I choose c2 equals -5, if I choose c2 equals -5, it will be -5x squared. And c3 is already chosen, so which is 1. So 1 times 5x square is 5x square. So this will be negative 5x square and this will be 5x square. That will be cancelled out and it will be 0, right? So then if I choose C1 equals 2, C3 equals 1 and C2 equals negative 5, then C1 times 2x plus C2 x square plus C3 5x square minus 4x will be 0, right? So we can say that this 2x x square 5x square minus 4x is linearly dependent, because we were able to write it in a linear combination which is equals 0 and all these constants are not 0, right? So that's why this is linearly dependent. All right, so here we have three functions, but what would happen like n functions? Is it possible to check by this method? Is it easy? It would be very difficult. So we have a Wronskian method to check whether n functions are linearly dependent or independent. Okay, so let's look at Wronskian method. Let f1x, f2x, and fnx be n functions that are n minus 1 times differentiable. Then the Wronskian value of these functions is the determinant of f1x, f2x, fnx, f1 prime x, f2 prime x, fn prime x, and up to fn minus 1 prime. If the determinant of this, so this is called Wronskian of f1, f2, fn. If the Wronskian of f1, f2, fn is equals 0 on that interval, then we say that these functions f1, f2, fn is linearly dependent. If this is not equals 0, then we say that f1, f2, fn is linearly independent on that interval. So if you find the determinant of these values and then check whether this is 0 or not, then that will help you to find whether those functions are linearly dependent or not independent. Okay, so we will use Wronskian method to check linear dependent or independence. Okay, let's take an example. So it says use Wronskian to determine whether the set of function is linearly dependent. So here we have a set of function y1, y2, y3. Okay, so I'm going to find Wronskian of, let me use different color. So I'm going to find Wronskian of y1, y2, y3. Okay, so the determinant of sine x, so just write down whatever the functions are in a row and then find the derivative. Sine x, the derivative of sine x is cosine x, derivative of cosine x is negative sine x, and the derivative of 1 is 0. And because there are three functions, so we should have 3 rows. Okay, so it should be n by n type of determinant. And now let's differentiate cosine x. It will be negative sine x, and the derivative of sine x is cosine x, so it already have that negative sign, and the derivative is 0 is 0. Now the determinant. So to take the determinant, you can search the method. You can review. I'm taking this column because it has 0 0 here, so it will be easy to determine. But you can take this rows or these columns, any columns or any rows. So it will be okay. So we need to figure out this will be plus, this will be minus, and this will be plus. So plus 1 times, if you take this one, then this and this will go out, and we should take the determinant of the rest. Okay, so it should be 1 times cosine x, negative sine x, negative sine x, negative cosine x determinant. And then again this will be here it will be negative, and this will be positive, and this will be negative. So how do we determine whether this will be positive negative, because you can see the position of this one is a11, so negative 1's power should be 1 plus 1, which is negative 1 to the square, so it will be positive. And its position is a12, so negative 1 to the power 1 plus 2, which is negative 1 to the 3, which is odd, so it will be negative 1. So that's how you have to figure out which, what would happen. Alright, so negative 0 times whatever, that will be 0 plus, okay, and then here it's turned, so 0 times whatever will be 0, so I'm not calculating anything inside the determinant. So this will be, that's why I took that column. Now the determinant of this would be cosine times cosine, this times this minus this times this, so negative cosine square x minus plus sine square x, so it will be negative cosine square x plus sine square x, and sine square x plus cosine x square is just 1, so it will be negative 1, which is not equals 0. That means these are actually the set of function is linearly independent. Thus the set of functions sine x cosine x 1 is linearly independent. All right, okay, so now we figured out whether the functions are linearly dependent or independent by Wronskian. Okay, so for example, let's look at here. This is the nth order linear homogeneous differential equation, because you can see this is 0. Then y1 y2 up to yn is the set of solution of this linear homogeneous differential equation, is linearly independent on I if and only if Wronskian of y1 y2 up to yn equals not equals 0, right? And any set of y1 y2 yn of n linearly independent solution of this differential equation is said to be the fundamental set of solution. So this will be called fundamental solution if they are linearly independent. And if these are fundamental set of solution of star on I, then the general solution of that differential equation will be this one, the linear combination of those linearly independent solution. Okay, all right. Okay, so let's look at another example. It says determine whether these set of functions are fundamental set of solutions of this differential equation and find the general solution. So to be a fundamental set of solution, those functions should be linearly independent. So we will check whether those functions are linearly independent or dependent by Wronskian. So Wronskian of y1 y2 is determinant of e to the 3x, e to the negative 3x, and I need to take the derivative. So the derivative of e to the 3x is 3 times e to the 3x, and the derivative of e to the negative 3x is negative 3 times e to the negative 3x. That's it. Because we just have two functions, so we just need to take the next derivative. So it should be 2 by 2. Now let's find the determinant. So multiply this times this, which is negative 3 times e to the 3x times e to the negative 3x will be to the 0 minus 3 times e to the 0 again. So it will be negative 3 times 1 minus 3 times 1, which is negative 3, which is negative 6, which is not equal to 0. That's why this e to the 3x and e to the negative 3x is linearly independent, and hence is fundamental set of solutions of y double prime minus 9y equals 0. Now let's find out the general solution. So the general solution is y equals c1 times y1, which is e to the 3x, plus c2 times y2, which is e to the negative 3x. So this is the general solution of that differential equation. Okay. All right. So far we were discussing about the solution of homogeneous linear nth order differential equation. Let's look at the non-homogeneous equation. So the general solution of the nth order linear non-homogeneous equation. So this is nth order linear non-homogeneous equation because g of x not equal 0. The general solution would be y equals complementary function plus any particular solution. So we always have two solutions, two types of solution. We usually denote yc, that means complementary function, plus yp, particular solution. So what is this yc and yp? Actually, this yc is general solution of nth order linear homogeneous equation. That means if we have non-homogeneous equation, first we set this equals 0, g of x equals 0. That will be homogeneous equation, right? And we will find the solution of that nth order linear homogeneous equation, and we will write that in a general solution form, linear combination form. So that is your yc. Now what is yp? Yp can be obtained by different method. It depends on what type of differential equation it is. So there are several methods to find the particular solution. Okay, so we will find that particular solution. We will see some methods to find the particular solution. So far, right now, let's just assume that yp is a particular solution of the non-homogeneous equation, and then we will add this solution to find the general solution of the non-homogeneous nth order linear non-homogeneous equation. Okay, so keep this in mind. All right, so let's just look at here. Let's say that yp equals this is a particular solution of this non-homogeneous equation, and yc is the complementary function. Then what would be the general solution of this non-homogeneous equation? So the general solution would be y equals yc plus yp, right? What is my yc? Yc is c1 e to the x plus c2 e to the 2x plus c3 e to the 3x plus yp is negative, okay, so I will use negative sign here, negative 11 over 12 minus 1 over 2x. So this would be the general solution. I just added them. Okay. All right, so again, let's just review here. Okay, nth order linear non-homogeneous ODE is this ODE where g of x not equals 0. Now we already know that by superposition principle, the general solution of the homogeneous linear ordinary differential equation is this one. Okay, if y1 and y2 are the solution of homogeneous linear ordinary differential equation, then the general solution would be the linear combination of those two solutions, right, by superposition principle. Now by superposition principle for the non-homogeneous linear ordinary differential equation, again the same thing. All right, so let's look at if L of y. So L is the differential operator which we have already discussed earlier. If L, so for example, you can see this is my L of y. Okay, the left side, the whole differential equation of the left side, that's my Ly. If L of y equals z1x, let's say that this is your z1x, has solution yp1, and L of y, that means the same Ly, the left side is same. Okay, but you can change that g of x, with a different g of x. Let's say that is your g, the left side is same, the differential equation is same, but the right side, the function on the right side is different. Let's say that z2x, okay, has the solution, the particular solution, let's say that yp at 2, yp2. Then the non-homogeneous linear ordinary differential equation of this form with Ly, that means the left side is this one, equals c1 times z1x plus c2 times z2x. I just changed this right part by this value, okay. Then the solution of this non-homogeneous differential equation would be as the solution of this one, yp equals c1 yp1 plus c2 yp2, okay. All right, so that is called the superposition principle for the non-homogeneous linear ordinary differential equation. So you should keep this in mind, okay. So for example, let's look at here. Suppose we have a non-homogeneous ordinary differential equation, non-homogeneous linear differential equation. This has a solution yp, and again another non-homogeneous linear differential equation has a particular solution. This you can see on the left side. On the left side, this one is same for both equation, both non-homogeneous linear differential equation, right? So I can use this superposition principle to find the solution of this non-homogeneous differential equation, okay. So if we have these two solutions of these two non-homogeneous linear differential equation, then is it possible to use to find the solution of this differential equation? If so, find the solution. If not, explain why, okay. So I think yes, because let's say that this is my z1 of x and this is z2 of x. And is it the linear combination of z1 of x and z2 of x? Yes, because if I multiply this equation by 1/2, then that will be 3x squared plus 1. And if I multiply this by -2, then that will be this, right? So yes, we can find. So yes, it is possible to find the solution of this non-homogeneous equation. So y double prime minus 6y prime plus 9y equals 3x squared plus 1 plus 24 e to the 3x can be written as this way. The half of this one, which is 6x squared plus 2. The half of this will be this one, minus 2 times -12 times e to the 3x, which will be 24 e to the 3x, right? And which is actually 1/2. This is z1x minus 2 times this is z2x. So actually this is the linear combination of z1x and z2x. And on the left side we have the same differential operator. So we can find yp, particular solution of this one, which will be the linear combination of the particular solution of these two, right? So that will be 1/2, because my c1 is 1/2, 1/2 of yp1. yp1 plus -2 times yp2, right? So that will be actually, excuse me, 1/2 times yp1 is 2 over 3x squared plus 8 over 9x plus 2 over 3 minus 2 times yp2 is -6, excuse me, x squared e to the 3x. And I can multiply this. I will get 1/3 of x squared plus 4 over 9x plus 1/3 minus plus 2 times 6 is 12, x square e to the 3x. So this is the particular solution of this non-homogeneous differential equation. All right. So this is by superposition principle of non-homogeneous linear ODE. Okay. All right. Okay, that it is in this lecture video. Thank you.